double Raman scheme, which has shown interesting features like amplified reflection, phase conjugation, and oscillation without cavity. This is also very interesting with quantum effects like squeezing and spectral line narrowing. So recently there has been some interest on mirrorless parametric oscillation extending to terahertz domain with the intention to increase the efficiency at low light level. But the theoretical work has not been well established. Backward retrieval of a signal with high efficiency without cavity is only applicable for the stationary atoms. What if we have moving atoms, Doppler shift? That would require further theoretical work in order to understand the effect of collisional broadening and also thermal broadening. There are all these motion-induced dephasing will affect the spin wave momentum, and also it will compromise the noise in the system. So in addition to that, it will also affect the phase matching condition in the case of finite propagation, where you have length of material. There will be also multiple correlation of beams due to the higher order mixing of the wave. And we would like to make use of the cancellation of beam noise by intensity difference squeezing to establish low noise signal. So it will also help in narrowing the bandwidth of entangled photon. So this scheme will also help in narrowing the bandwidth of the entangled photon due to the counter-propagating scheme. So all these effects would be interesting to develop a unified full quantum theory. Regarding the applications that will be of interest currently is the having a theory that can describe quantum memory materials for quantum communication. So there are many candidates like cavity QED scheme, alkali gases, room temperature, and also ultra cold gases. But the most promising materials are diamond with nitrogen vacancy and also rare earth iron doped crystals. Because they have very narrow line width due to the screening of the some atomic shells that is not available in the atomic gas. However, there are some features in atomic gas that are more advantageous. So there is no single scheme that is good for quantum as a quantum memory materials. So there are, each one has its own advantages and disadvantages. So our focus will be on the simple atomic system that can be extended from cold gas, cold temperature to finite room temperature. So in our model, we will not include the phonon broadening at the moment. So this double Raman scheme is typically presented for the case of atomic gas, where you have a 3-level or 4-level scheme that is well defined. In the case of solid state, this model may not be valid. So this model has been used for quantum information storage of a single photon into atomic ensemble through the writing and reading. So storage of single photon and retrieval of the pulse. And in the middle of the interaction, we have the so-called dark state polariton. It's a mixture of spin and the photon. This model has been well established, but the noise aspect is not fully taken into account. And also there are limitations like counter-propagating scheme is the boundary condition is not properly taken into account. Another two important works in 2003 are these experimental demonstrations of the correlated photon pairs in double Raman scheme. One is in the group of Kimber using ultra cold gas, and another is in the group of Lukin using room temperature gas. So the room temperature gas scenario is very promising, as it is the setup is experimentally more feasible. So in our theoretical work here, we would like to develop a full quantum theory that can be used to describe quantum light for developing noise-free spectroscopy as well as quantum memory. So our model is expected to have impact on the experimental aspect as well as investigation into squeezing aspect with a counter-propagating light and quantum light source used in spectroscopy. So this model is well known. We consider a 4-level system, the 2 ground levels B and C, and upper D and A. And we have coupling of the free Hamiltonian is for the atoms, 4-level atoms, and the vacuum radiation. And the interaction is there. There are 4 interactions here. One is due to the palm laser, and this is the Stokes, the quantum field. With the head is the operator, and this is the control field, control W frequency, and you generate the anti-Stokes quantum field. And this 4-level system is coupled to the Maxwell equation in slowly varying approximation in one-dimension propagation. So in this scheme, in this one-dimensional propagation, we can have 4 possibilities. The first one is the 2 laser fields and the quantum fields are all propagating the same direction, positive Z. The second one is where the quantum fields are counter-propagating to the laser coherent fields. And these are considered as forward geometry. And these are the only possibilities because they the first one is feasible, but the second one is not feasible because it does not satisfy the phase matching condition. For the backward geometry, you have the thumb and the control lasers are counter-propagating. And there are now two possibilities. The Stokes can propagate along the same direction as the palm. Another possibility is it can propagate counter-propagating to the palm, and the Stokes is opposite. So these are the two possibilities. In the model, it is important to take into account the phase of the lasers, the palm and the control, as well as the quantum fields, because there will be a phase. In the case of Raman scheme, you have a relative phase between any two fields. Otherwise, it will average out and will not give any effect. And the phase matching is due to the dispersion of the material. So there are some novelty of our work here is that this is a counter-propagating quantum approach, and we are computing the two-mode squeezing. And we have identified that for the backward case, we have a resonance region that give rise to mirrorless amplification. And we have also found the violation of Cauchy-Schwarz inequality and also squeezing, two-mode squeezing for certain parameters, of certain laser parameters, and also propagation length. So these are unexpected findings that would help us understand the quantum nonlinear optics system even better. The couple equations to the Maxwell propagation equation in one dimension is governed by this relation, where you have a quantum field is connected to the Langevin operators of the coherences. So here we keep it general, where this can be positive or negative, but take into account the forward and the backward propagation scheme. If we calculate the Hamiltonian from the Hamiltonian using the Heisenberg-Langevin approach, we have this full couple equation, 16 Heisenberg-Langevin equation with the noise operators F. And we have to use some approximation to solve, because it can't be solved exactly. We have to linearize so that there will be terms with the product of atomic operators and the quantum field operators. We have to approximate in this manner and take this as a steady state, and so that the term is only linearly proportional to the quantum field. So these equations will be reduced to a steady state solution with the population diagonal elements, so that they can be solved exactly analytically, and this will be used in our to fit into the other half of the equation. After solving this couple equations, we we can get the steady state coherence like rho AB, rho DC in terms of the population and also the inversion, population inversion here. And all the complex decoherences that include the dephasing, decoherence, real part, and also the complex, the imaginary detuning, they are included. So the other remaining part that contain the quantum fields that form a closed couple equations, they are these four equations. So these four equations, notice that they are all linearized because there is no product of two operators. Here is only one operator, and this one operator. We have taken this as the average. And then we always keep all the noise operators. So the noise operators are important, cannot be neglected because it will be inconsistent with the fluctuation dissipation theorem if we neglect the noise operator. Because the gamma must be accompanied by the noise operator. So to solve this, we can make a Laplace Fourier transform of all these four equations, and then we solve algebraically. We in the Q space from the position Z and T space, we transform into the Q and nu space. So this is the Stokes field in the transform phase, Laplace transform. It means we make a Laplace transform on the position and the Fourier transform on the time. So this is as a full solution that contains the initial boundary condition of the Stokes and also the boundary condition of the anti-Stokes, as well as all the Fourier transform of the noise operators. So if we take average of this, we are able to get all the linear and non-linear susceptibilities, first order and the third order susceptibilities for the Stokes field and also anti-Stokes field. This Q factor is actually the Fourier transform parameters. We have to keep this later if we want to transform back to time or space domain. This will be a variable, and they are all different for all the different cases, forward and also backward. So now, if we take the definition of the polarization, this is a polarization for the anti-Stokes and for the K component of the XYZ. So K can be XYZ. And we can write in terms of, we can have the susceptibility tensor, linear susceptibility, and this is the non-linear susceptibility. And from here, we can extract the chi1 and the chi3. So this is the expression for the chi1, and this is for the chi3. And if we neglect the nonlinear terms, we will recover the the expression for EIT. Okay, and for this chi3, we will also recover many general expression for the forward mixing process, Raman process also. And the coefficient is quite complicated. The coefficient given here, this W and N, is given in the general solution here. Yeah, these are all the general solution. So the expression for W and N is given by all these laser parameter and also atomic parameters. So this is the Raman term that shows the phase, relative phase must be preserved. So in the case we set the pump field to 0, we will get the expression for electromagnetic induced transferency. And this is the third order susceptibility. We can also get that when we set I and P. This is actually the I is correspond to omega square wave frequency square. So we can also write the solution of the couple equation with in this parametric oscillator form. Okay, the four solution of the atomic solution and the couple to the Maxwell equation, we will be able to get this. This is a generalized noise that includes all the noise operators or contribution for the four coherences. This is the Stokes operator, this is the anti-Stokes operator, and the G and K scripts are they given by this expression. So the number density of the parametric oscillator is inside this G and kappa, is inside the kappa here. So G is the coupling constant of the quantum field. So everything all is inside. So we have to solve for this couple equation with the boundary condition. By using Laplace transform method, we are able to get general solution for all the four cases, forward and backward propagation. So there are two parts. The first part, it depends on the boundary condition. And the second part with the integral contains the noise operators. This is the general one. We have used it to compute all, to obtain all the solution for all the four cases, for the especially the backward propagation. And this cascade symbol is contain all the spatial propagation term, which is expressible in terms of hyperbolic cosine and hyperbolic sine. And we also found useful relations that relate this cascade of function. And for convenience, we will define this big capital pi, because this term appears quite frequently later. Okay, so for the case A, this is the solution. This is the simplest solution. The boundary is at the 0, and then we can find the solution at any point inside the amplifier or material, any position Z. And this is the Q is the root of the plus and minus is the root inside this pi, and the pi and cascade are given previously here. Okay, so this is Q plus, Q minus, they are the roots, quadratic roots given, and the roots are expressed in terms of the gain and the coupling, the script G and the script K. Okay, so we can write in this form, we can in the same form like define the psi function. You exactly the same, except that you have a non-local space dependent defined by eta. Eta equals to so this is z, z minus s. Okay, now For case B, forward propagation, is where the boundary field is now at the L, at the position L, at the other end of the, instead of the at the beginning. So there's the difference. So we have to express the solution in terms of SL and AL. So we have to solve, we have to replace this in the former by this expression. The former equation, we have to replace S naught, A naught by these two equations. Then we will have a general solution written in terms of SL and AL. Okay, now the main solution is here, the backward geometry. So for the backward geometry, first case A, we will have, this is the first equation we write. Later we have to solve, we have to write in terms of S naught, but we have to write as in terms of A dagger L, because the Stokes start from 0, at Z equal to 0, and the anti-Stokes starts from Z equals to L. So we have to specify the boundary fields at different points of the medium, opposite points of the medium. And J is the integral of the function with the noise operators. So this is how the solution looks like. The Stokes field at any point inside the medium is expressed in terms of the boundary Stokes at the Z equals 0, and the anti-Stokes at the boundary Z equals to L, plus the integral over all over the noise operators. So this function inside is given by, inside the integral is given by all these four. There are two parts here. One is has to be integrated up to ZS. That means any position you specify within the medium. But while this one has to be integrated up, can be integrated from S up to L. So the limit is different for these two, because it is taken care of by the Heaviside function theta here. So the opposite case, where now the Stokes is propagating to the negative direction, while the anti-Stokes is propagating to the positive direction. This is opposite from the case 2A. We will also get the same similar form of solution, except that now we express in terms of A naught, and then here SL. Okay. And we have to check that these two, the solution for 2A and 2B are symmetrical. By interchanging the variable, we will get the same form, to make sure that our solutions are correct. So we have checked that. Okay, so from this counter-propagating solution, we can analyze the solution and we can get resonant effects. So there are terms that appear in the denominator here. So with this, if this no denominator vanish, okay, for the case 2B, it will be pi minus. For the case of the first case, 2A, it will be pi minus, but S. This is Stokes. Okay. So they are different. One is Stokes, one is anti-Stokes, but they're still both are minus. So we let us analyze, say, by taking this the case 2A, we set this close to 0, then we will have this solution. So this is a resonant condition. If the denominator is small, then the signal will shoot up very large. Of course, it will not go to infinity because all the variables are complex. So there is no, if it is real, completely real, then there will be singularity. But they are all complex, so there should be no problem. So here we can estimate the length of the resonance condition LR. So based on this expression, so it is dependent on the beta, which is dependent on the script G and the script K. So everything is governed by the script G and the script K. Will determine the resonant length. So at this resonant length, very interesting features appear, as I will show in the simulation. Okay, from all the solutions, we can compute the G correlation function, the fourth order electric field. Instead of writing in terms of electric field, we write in terms of S and A, which are actually in the unit of frequency, or same unit as Rabi frequency. So we have to divide by this cupping constant square. Okay, it's just for convenience, but the definition remained originally the same as Roy Galber's definition. So this is the cross correlation between anti-Stokes and Stokes, and FF. This is the self correlation for the F equals to Stokes or anti-Stokes. In the evaluation of this, we have to notice that this term vanish in the case of thermal photon. But if you are dealing with squeeze vacuum, then this situation becomes much more complicated. This term must be evaluated. So from here, we can compute the Cauchy-Schwarz correlation function by normalizing this. If this parameter is much greater than 1, then we have a very large non-classicality. And the self-correlation at the time 0 or 0 delay is related to the Q parameter, to the Mundell Q parameter. Okay? And so it is related to the Poissonian. We can study the effect of Poissonian or sub-Poissonian effect by computing the G2 at time delay 0, as well as the Q parameter. Okay. So now this is the new parameter that we are computing because it's connected to the experimental work of squeezing. We have submitted the work and is still under review. So in the experimental work, they have shown that for certain parameters, it is possible to get non-classical squeezing effect. So this work will help to understand the experimental work. So this is just a difference between the two anti-Stokes and Stokes photon number operator. So we can rewrite in terms of the normalized correlation function G, and also in terms of the Q parameters. In the case where tau equals to 0, we can write in this manner. So all terms are positive except the second term here. For this quantity to be non-classical, it has to be less than 1. That means this term has to be larger than this, the first term. Okay, so that means the G2, the cross correlation must be large enough so that we will have squeezing. So the G2, so this cross correlation is extremely important. It tells a lot. If we have a large value, that means we were likely to have a non-classical effect. Okay, here are some subtleties that we are discussing between the concept of anti-bunching and the sub-Poissonian. These are some subtleties. We just make this very clear, because otherwise there will be some confusion or misunderstanding. Because now we writing it very clearly here, spell out clearly. The subtle difference here. Okay. Okay, now we show some result of the simulation under different laser parameters. So Raman EIT scheme is where there are two double Raman, okay, double Raman transition. The first Raman is spontaneous Raman, off resonant Raman. The second Raman is the resonant Raman, which form the EIT scheme. So that's why it's called Raman EIT. So one is off resonant, one is resonant. This is REIT scheme. Okay, and we get this Chi1, Chi3, the real part and imaginary part, corresponding to Stokes and corresponding to anti-Stokes, and we can learn a lot from this analysis from the figures. We can see that these two figures are the same. And also we can study the symmetry properties for different Raman scheme later, resonant and off resonant later I will show. This is the big phi here and big psi. These are actually all the Fourier transform of the correlation function. Fourier transform of the correlation between Stokes and anti-Stokes. This is Stokes with anti-Stokes. This is anti-Stokes with Stokes, and this is the Stokes with Stokes field. This is anti-Stokes with anti-Stokes field. Yeah, it's not very clear at the moment. I think I would just skip this. We will focus on the G2, this consciousness inequality. This shows very large number. Here means highly non-classical. And you have oscillation, anti-bunching also, but only at very small distance, very small propagation length. If you increase the propagation length, then the oscillation will be damped out. Also the non-classical effect will go down. The squeezing also, different squeezing is actually the inverse. It's in a way inverse. So this part is very large non-classical and correspond to here. And we have also intensity of the Stokes and anti-Stokes is very small. So at very small quantum field photon number, we have non-classical correlation. And also at very small propagation length, we have non-classical. When we want to have a large number, photon number, or longer propagation, the non-classical effect would almost vanish. So we have to. So it's not easy to get non-classicality at high field. Okay, now with our solution, not only our solution can find the the field at the end of the material, but any point in the material. So for example, midway between the middle of the at the middle of the material around 0.5, we find the correlation will look like this. It will increase if the L increase, but it will not be as large as before. So the earlier one it will give much non-classical correlation. So so we can learn that the correlation inside the material is not big. Okay. Now, if we consider this so-called Raman resonant doublet, that means the two transitions are resonant. The two Raman transitions are resonant. So theta delta equal to 0. So we can we can find the susceptibilities like this. They are in a way is different from the third order, but is we can learn about the dispersion for the linear part, the dispersion and the absorption part. And here, the G2 correlation is not very big, but it is interesting. We can notice at certain length, periodically you have a resonant effect. Okay? Not only the resonant effect, but also the coherence is sustained towards a long time. And okay. And this the location of the peak can be explained by the analytical formula we obtain. Which is based on this expression. For the case of the same, for the for the resonant case, where the two laser fields are the same, we can get a very nice analytical expression. And notice that if we know all these parameters, these are all atomic and laser parameters, then it will repeat itself by the integer of m. M is so that explains the periodicity of the peaks here. And we have checked that the formula well describes the separation between the peaks. We have compared the forward and backward case. In the case of forward, there is no such resonance versus L. So all those peaks, they are for backward propagation geometry. Okay, backward. Only we will see all these periodic peaks appear as a function of L, this length of propagation, only for backward. For the forward, there is no such feature. So this shows, with this analysis, we have a very interesting resonance effect due to backward propagation geometry. That has not been found in earlier works. Okay, now the final limiting case of the laser scheme is both Raman transitions are off resonant. So we call it Raman off resonant doublet, ROD. Okay. As we also plot the linear susceptibility and non-linear susceptibility, and here in this case we can analyze. We see they are the same for the Stokes and anti-Stokes. See, but this for the third order, but for the first order, they are shifted. They are symmetrical, reflected to positive and negative frequency. So this symmetric, whether it's odd symmetric or even symmetric, we have analyzed it, and it is something that give us new understanding of on the dispersion and linear and non-linear dispersion that depend on the laser fields. Okay, for this off resonant, there is no interesting feature. That we have a very small non-classical correlation. So the interesting one is the resonant case. Okay, so we have plotted to just for completeness. We also plotted the correlation at midway. It shows that the correlation become also very small. Even if we stretch the length of the medium to very large, we don't see anything interesting. Okay, for both forward and backward geometry, they are all essentially the same, no effect. So the distinction between forward and backward geometry is found only in the case of both Raman transition are resonant. Okay, so this is what we found. Yeah, and we also study the effects of, we change the laser detuning laser parameter. There are now two parameters, laser detuning for the pump and also for the control laser field. So we simulated all these figures, forward and backward versus detuning of the control field. And this axis is actually the spectral frequency, and this is the laser detuning. Okay. So I will skip the details here. There are a lot of, in the case of correlation function and also squeezing, we also plot versus the detuning. And there is no effect of the detuning. Okay. Yeah, now we have new interesting effect in the case of resonant Raman, where the two laser fields are resonant, okay, almost resonant, because in this case we are going to vary one of the detuning, so we cannot say both are resonant. So one is resonant, another one we change the detuning, okay. So at certain detuning, we can see that we have a large negative here, means non-classical squeezing. And the correlation here, we can see some dip here, but it's not the large correlation. Okay. This is the Cauchy-Schwarz inequality, violation of that. And then here we see a more interesting feature. This is the G2 correlation. The G2 correlation shows the two regions here, that is persistent. It's not damped. So at this resonance, you can say that we have a persistent correlation that can overcome the decoherence. No decoherence will affect it. This is an interesting feature. Also at the resonance here, we can there are some laser parameter that can explain the peaks that happen here. Because if we zoom in this peak and this peak, we will see final. So around delta P equals to 10 and around 13.3, which correspond to these two peaks, we can see even finer details. So this peak is actually composed of twin peaks. Okay, And here you have the asymmetric peak for 13.3. So the interesting features are happening in around here when we vary the detuning. Okay, here we have different parameters. We just skip this. Okay, finally, if we, in the case of off-resonant, we have some non-classical feature, but this is not, it does not correspond to the last non-classical correlation. The coefficient violation is still very small, less than 2. So this, we cannot say the correlation is non-classical, but we can say the squeezing is non-classical here. So the different measure of non-classicality will, some certain measure will show non-classicality. The other measure will show there's no non-classicality. So it depends on what we look at it. So there's no a single recipe for quantum measure of quantumness. Okay, so to make a complete analysis of the whole system, we plot the all these possibilities versus pump detuning versus Rabi frequency for a pump, and also for the vary with the control. So these are all the possibilities we explore to see how this is the quantity that we explore the propagation, normalized propagation length. This is the log of the squeezing parameter, and this is the intense log of the intensity. So we see all these interesting features. When we change the detuning and the Rabi frequency, there are three possibilities here. We have we vary in this case, this label means we vary the pump, we fix this control, and then we vary the omega p, but we fix this. Okay, and then in this case is a reverse. Instead of p and Rabi frequency of p and c interchange, and then in the final case we keep the two Rabi frequency the same. So these are all the possibilities we explore. Okay. Okay. So the detail actually you need a lot of concentration to really describe it. I would not overshoot the time. If you have any question, you can we can discuss. So here to conclude, I presented. Okay, this work has taken a long time of very careful concentration to proceed all this subtle calculation during the pandemic when we were locked up. Uh, so backward propagation geometry with finite length composed of four level double Raman scheme valid for arbitrary detuning and intensity of a pump or control laser show interesting resonances. So we have developed a quantum Langevin theory that can describe all this. So systematic and we have done systematic and comprehensive analysis describe all the features in details, and they are affected by all the features, how we are affected by control laser parameters and also propagation length. So this it provides some insight on the condition to enhance and control non-classicality. So hopefully this work is can be useful for low noise non-classical light, for developing low noise classical light, non-classical light with quantum spectroscopy, and also as a very important theoretical foundation for quantum metrology, spectroscopy, as well as quantum memory that we are working on to have a robust theory for quantum memory scheme. Okay, I hope there's a lot of detail, a lot of technical thing. I hope it will be accepted soon, and then the result can be shared with everyone. Thank you so much for your attention. Okay.
Thank you very much, Professor Ooi. We have questions. Let's see, there is something in the chat. I hope it's a question. Yeah, okay. This was not a question. This was just somebody.
Thank you.
It was a very interesting talk connecting Raman and other issues like EIT and all that stuff. It's very nice.
Also, I have a question.
Sure, please go ahead.
You see, Chief Professor Ooi, first of all, wonderful talk. See, my question is that what are the major differences between Stokes and anti-Stokes for light? The photons which are coming from Stokes or the ones which are coming from anti-Stokes, what are the major differences?
Basically, the two are different. One is different in frequency. Normally, the anti-Stokes frequency is higher than Stokes. Okay, but the important differences are are generated by the pump laser, and the anti-Stokes is generated by control laser. So if the two laser fields are the same, then essentially they are no different. They are symmetrical. They are the same. But if one laser is stronger, or the detuning there is a detuning difference between the pump and the control laser, then the Stokes and anti-Stokes become different. Yeah, by symmetry, they can be the same, or they can be different depending on the detuning and the radio frequency of the lasers. Yeah.
Okay. Is there any big difference between the G2 values? Behavior of G2.
In a G2, let's say we have computed GAS, which means the correlation between the Stokes after we compute. What is if we were to compute the correlation in a reverse manner? Okay, we have computed like this GAS. If we were to interchange GSA, then for the scheme of Raman EIT, where we get very large.
Somebody has
somebody.
Where we get very large. In this case where this is GAS. I can magnify. Okay, this is GAS. Is very large. This is a Raman EIT. It is asymmetric because the first Raman is off resonant, and the second Raman is resonant. So the Stokes and anti-Stokes are now different, very different. So this what's the probability of detecting anti-Stokes after detecting Stokes? And it's the correlation, non-classical correlation is very large. But if we compute for this scheme, if we compute GSA, then the opposite. It means we will get very small non-classical correlation. Essentially, the correlation is no correlation or very small. Yeah.
Thank you. Yeah.
So that is the difference. But for the case of the two Raman transitions are the same, both are resonant or both are non-resonant, or then the GAS will be the same as GSA. Will be the same. Yeah, the correlation will be the same.
Yeah.
But both will be very small, or smaller than this. So the non-classical correlation for this Raman EIT is the largest one, the largest we can get. This is the largest. Yeah.
Would the Stokes and anti-Stokes keep on exchanging their energy between them in time? Like Stokes decreases, anti-Stokes increases. Does it happen or it would not happen? Because pump is driving.
Yes. Yeah. In our parametric equation, the Stokes and anti-Stokes are coupled together. That both fields are exchanging energy with each other. They have a feedback loop between each other through the parametric equation.
Correct. That's what I would have intuitively expected. Sine cos.
This couple equation. They are couple. Yeah. But we assume the laser fields are not depleted. Yeah, in this case.
Okay.
Yeah.
Prashant, long back you had done some soliton kind of solutions where you had a sin h cos h kind of thing where it was exchanging energy. So maybe these things have some similarities probably.
Yeah, that is true. There may be some similarities. Right? Yeah. Yeah, exactly.
So soliton, I guess, you will have a non-linear Kerr effect term, right? Diffraction term there. But we have not included the diffraction term, the non-higher order term.
I look at it more carefully. Thanks. Yeah.
So we don't seem to have any more questions. Probably for the students, participants, it's kind of, they're more worried about their dinner.